In this chapter, we'll discuss the alpha substitution reactions on carbonyl compounds. Tautomers are rapidly interconverting constitutional isomers. The best known example is the keto and the enol form of a ketone and aldehyde. Here, an example is shown with a ketone. The keto tautomer is on the left and the enol tautomer is on the right. If we count the number of atoms and the types of atoms in each of these two tautomers, we'll find that they're constitutional isomers of each other. And what makes them different from other constitutional isomers is that these two are rapidly interconverting. In general, the keto form for most carbonyl compounds will be favored. As an example, for cyclohexanone, close to 100% of all molecules will be found in the keto form, and for acetone, even more so. There are a few examples where the enol form is favored over the keto form. This is seen with 1,3-dicarbonyl compounds. For example, if we have a 1,3-diketone as shown here, about 8% of all molecules for this compound would be found in the keto form, and close to or around 92% of all molecules would be found in the enol form. What makes this different from other carbonyl compounds is that the enol form here has conjugation. So this double bond is conjugated to the carbonyl on the left. Conjugation means that we have alternating double, single, and double bonds. That adds extra stability to this particular structure. In addition, we have an internal hydrogen bond, which you can see here between the enol form and the carbonyl form for the other carbonyl. That helps stabilize the structure as well. Another example where we see the enol form being favored is a compound such as a phenol. As we see here, this compound is aromatic, and aromatic compounds have a lot of stability. In fact, they're more stable than your typical conjugated alkenes. We'll learn more about aromatic compounds and aromaticity and how it stabilizes compounds later in the semester. But for now, you can also think of this phenol as being conjugated as well. So that makes this compound, this enol form, more stable. Over 99.9% of all molecules will be found in this enol form. Tautomers can interconvert rapidly under acidic or basic conditions. We'll first look at the mechanism for the acid catalyzed tautomerization of a typical ketone. So starting with a ketone, the carbonyl oxygen will be protonated by an acid, leading to this structure. So this is a protonated ketone, which has another resonance form, which we can draw by taking the electrons in the double bond and sending them to the oxygen. That results in a positive charge. Instead of the oxygen being on the oxygen, it will be on the carbon. Base can then remove the alpha hydrogen and place a double bond between these two carbons. Notice that leads to the enol form of the ketone that we started with. Carbonyl compounds can also tautomerize quickly under basic conditions. Under base catalyzed conditions, a base would remove the alpha hydrogen, which is the most acidic hydrogen on a carbonyl compound, leading to a negative charge in the product of that reaction. So note that what we form is called an enolate. Enolate is the conjugate base of a carbonyl compound. We're going to discuss enolates in detail in this chapter. Enolates have two resonance forms. So if we take this negative charge and move it here, we can put a double bond there. And if we move the pi electrons from the carbonyl to the oxygen, we will have now a single bond there and a negative charge on the oxygen. So these are the two resonance forms of enolates. You can use either one to protonate the enolate and move on. So for example, the oxygen can be protonated by water to produce the enol that is shown here. The enol and keto forms of carbonyl compounds are probably the best known tautomers, but there are other tautomers known. In fact, tautomerization is an important process in understanding the chemistry of DNA bases. We can see on this slide that guanine, for example, has a keto form, which is shown on the left. So it is essentially an amide. And there's also an enol form, which we see here in this structure. There's also a keto and an enol form for thiamine, as shown here. There's an amide shown on the left, and there is an enol form on the right. There's also two different tautomers for adenine and cytosine. So there's an amino form and an imine form, which we see here. Same thing for cytosine, an amino form and an imine form. Before the 1950s, many textbooks would show guanine and thiamine in the less favored enol form. It was a crystallographer Donahue that suggested to James Watson to use the more stable keto form of guanine and thiamine, which later helped them develop the 3D structure of DNA that we know today. So by using the more stable keto form of guanine and adenine, we can draw the base parent that we see on the screen here between guanine and cytosine. So it involves three hydrogen bond interactions. And then using adenine and thiamine in the forms that we see here, we can have two hydrogen bonding interactions as shown. To review tautomerization, let's go over this question where we're going to try to draw the enol form of cyclopentanone. The enol form of cyclopentanone looks as shown here. So we would take one of these alpha hydrogens and remove it, place a double bond as shown here, and then add an OH or a hydrogen to this oxygen of the carbonyl, turning it into a single bond. And so this is the enol form. We could also draw the double bond towards the left. It would give you the same enol in this example, since the ketone we're starting with is symmetrical. Now, the second part of this question asks us to indicate which hydrogens are acidic or most acidic, I guess. So that would involve the four hydrogens that we see here. So that would be the four alpha hydrogens. There's two on this carbon, and there's two on this carbon.